In today's video, we're going to talk about word embeddings. What are they? Why are they important? And then we're going to build word embeddings from scratch. We'll start with something very basic, bottoms-up approach. Start with something very basic, use different techniques, and see how those different techniques perform. So we will evaluate our word embeddings as well. So this video is really meant for those who want to build a high-level intuition for what word embeddings are and why are they important, and also get a sort of a look at word embeddings in action. And so I'm going to be staying away from technical things as much as I can. I'll definitely not get into any kind of math and all that. I do have a code that I've already written that will help us sort of take us through the different ways of building these word embeddings, applying different techniques, and evaluating them. Okay, so I'm not going to code. It's already been coded. We'll just kind of run through it. So let's get going. Word embeddings are nothing more than a numerical representation of words. Okay, so we will unpack that. So as we go through this video, word embeddings, basically, a word embedding is basically a word vector, vector with a numerical representation for that word. And how we build that is what we will do in this video. I'll show you how to do that very foundationally, in a very basic way, and then we'll build up from there. Okay, so let's start with some illustrations here, right? Just to build some intuition here. So vectors, right? Here's an example. So we have two cars, A and B, and there are two elements about this car that we want to evaluate both of the cars against each other on. So the first element is the price of the car and the miles per gallon. And let's say for car A, it's $20,000. For car B, it's $22,000 miles per gallon. We're going to get, let's say, 20 here and 21 here. And so essentially what we've done is created a vector A and vector B with two dimensions. Dimension 1 is price, and dimension 2 is miles per gallon. Okay, and so anytime you got vectors, you can represent them. In this case, there are two dimensions, so we'll draw a two-dimension space here, basically XY coordinates, right? So let's say this is 20, sort of like 30, something like that. 20, 30. All right, car A is 20 and 20, so it's something like this. The other guy's 22 and 21, so it's here. Car B, car A. Okay, so again, building intuition. The distance between these two guys, right, is how far they are, and in this case, they're kind of close together. And let's say if we had I'm just going to make this up so we can see everything's relative. We had some other car which was here, car C. Just looking at this space here, we can see that both cars A and B are further away from C than, and they're close to each other, but they're further away from C, right? So just building up some intuition here. All right, and so now we'll go a little deeper here, meaning give some examples that hopefully keep building on this intuition. So words, before I do that, a good reminder, words are related to each other. There's a semantic relationship, right? A word can also have different meanings. And what I mean by that, let's take the word bank. Let me give two examples. The first one is, I went to my bank to deposit a check. Well, here the bank is a physical building in which I went to deposit my check. Another example is, I went to the river bank, right? Here the word bank has a whole different context. The point is, in each one of those sentences, right, we can determine the relationship between those words and what they mean, and that's what human beings do, right? So we kind of we can understand, like, the word bank in both sentences have a different meaning, right? And so if we had a word embedding for every single word in the English language, then we would expect that in a two-dimension space, let's assume that every word in the English language has a two-dimensional word vector, word embedding. And then if that was the case, and if it was built in an optimal way, what we would find is the word orange, let's say, is randomly plotted here somewhere. We would find that the word embedding, the word vector for color, might be somewhere here, and the word embedding for the word fruit might be, let's say, somewhere there. Because the word orange, we know that as a color. We also know orange as a fruit, right? But let's say some word like steel, right? Orange is going to be much further away from here, from the word steel, because it's not that that related to the word steel. But orange is much more related to color and fruit. Okay, so if the word embeddings were built in a very optimal way, this is what we would see. And when we go through building our word embeddings, we will get pretty close, right? And so you will see this play out. So it's the word relatedness. So this word embedding should pull the words that are similar or have a relationship closer together. In this, in our case, two-dimensional space. In reality, obviously, this word embeddings have many more dimensions, and we really can't pictorially illustrate that. But this should build an intuition for what word embeddings are, and their numerical representation of the words. And if they're done correctly, this is what should happen. All right. So then let's start with how to further unpack this. Let's say I am going to randomly sort of come up with a sentence here. Let's say we have something like this. Let me scroll up here. Let's say something like data scientist will use Python for machine learning models. Okay, so words are related, and so in this sentence, if we hone in on the word Python, let's think of that as our context word. The word Python in this case, from this full sentence, we know because of words like machine and learning and data scientist that in this case it's referring to the programming language Python and not the Python that one might find in the jungles, right? So again, it's the context, the words that are around it tells you what it means and how all these different words are related. So in building word embeddings, the most basic foundational way to build word embeddings is to create what's known as a co-occurrence matrix. And basically what that would be is a matrix. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9 words. We have 9 words in this sentence that I've written. So it will be a 9 by 9 matrix. So for each word from 1 through 9, let's say word number 5 is Python and word number 1 is data, right? So what we want to see is that the word Python here, how closely is it related to the word data, right? And so, well, it's subjective, like how are we going to determine that? So in order to do that, there are 2 things we have to think about. One is the window size, and the second one is scale. Why do I say this? Because if I want to understand the relationship between Python and all the other words in the sentence, I can control the size of the window. So hey, do I want to understand the context of, given the context word Python, the relationship for the words just left and right of it, or two words to the left and two words to the right? In that case, the window would be 2, or 3 words to the left and 3 words to the right. Okay, so window size is basically how you want to find that how words are related based on how close they are, right? So from how far is machine from Python, it's 2 words away. So window size was 2. We would learn the relationship between Python, word 4, and machine. If the window size is 2, we would learn the relationship between Python and use and will, because you got to go both left and right. And so let's play this out. And our context word is Python. If our window size is 3, now scale comes into play. So how do you want to equate the relationship between the word right next to it, adjacent to it, or 2 words away or 3 words away? Do you want to give it the same value, that Python is just as related to the word 4 as it's to machine as it's to learning, if we're using a window of 3? So the flat scale, so the first way you can scale is just a flat scale. So you're going to give equal importance. So you're going to say the word 4 is just as important as machine and as is learning. And we also go left this way. Okay, so they all get a value of 1. So if that's the case, the second word here is scientist, right? So what would happen is Python and scientist, right? In our way of creating this co-occurrence matrix, we would say, since we're using a window size of 3, we would say the word scientist and the word Python, we're going to give it a value of 1, right? Because this is 1. And the word number 3 would be will, also would get 1. And so that's how we start to fill the matrix out. Okay, that's one way to do scale. Other way to do is, obviously, you can do something like 1 over n, actually scale it, because you might not want to give machine as much weight as you want to give 4, because 4 is right adjacent to the word Python and machine is like one word further away. So if you want to scale it, and let's say we still use a window size of 3, then we just by default give Python a value of 1, and so that way it's going to be related to itself. And in this case, we're going to scale it, and so the word right next to it will get a full value of 1. As you move one word further away, in this case it'll be 1 over 2 and 1 over 3 for learning, because it's the third word. And you got to do the same thing here, going left. So in this case, what would happen is that if we were doing this, then the values that we would fill out here is that for Python, in the word scientist, which is the second word 5, it would be 0.33, 1/3. And then this is the word data scientist will, here it would be 0.5, etc. And the next one would be 1. Okay, and that's how we would populate the co-occurrence matrix. And obviously this is just one sentence. When building word embeddings, we would use a lot more text, and perhaps there's like 5,000, 50,000 sentences, right? So we would go across each one of this and do this calculation, and depending on the text, 50,000 sentences, the word data may show up in many different contexts, and we would, through the co-occurrence matrix, we would build that relationship with the word data and all the other words that surrounds it. Okay, essentially that's it. So the key thing to keep in mind is that the most basic foundational way to build word embeddings is create this co-occurrence matrix. Essentially, you want to see how these words co-occur. And so in our example here, the word Python co-occurs with all of these words, but depending on your window size, you're going to limit the co-occurrence window. And so, if you with 3 window size of 3, you have to go left and right, and then either you can keep it flat, you have to scale it, so you either keep scaling flat or actually 1 over n scaling. Okay, so that's the most basic foundational way to build word embeddings. And that's what we're going to do next. And I'm going to take us to where my code is. So I've already written this code, and so that way we can just go through it. What I had done, because in our simple example, it was one sentence, and I said in reality, the way you build word embeddings is you take lots and lots of text, so you can really pull that relationship between words together, right? So in order for the word orange and the fruit and the color to be close to each other, we would have to read through a lot of text to understand over and over and over that, hey, orange is a fruit and orange is a color, right? So that's the basic idea. So in this case, I have downloaded this data set from CFPB's website. This is publicly available, Consumer Financial Protection Bureau's website. This data set contains complaints from U.S. customers who are filing complaints against banks for whatever the reason may be. So I used some time period and it had like 400, so I don't know, 40,000 complaints in there. So I just took a 1% sample because my computer's not all that powerful. It would take a long time to process 400,000 plus complaints and convert that into a word, into a co-occurrence matrix. So all this work has been done. So let me just show you here. Let's see. Just to show you, 435,808 complaints in the original download that I did, but I'm only taking 1% of it, so 4,358 complaints. And then what I do, well, before I do that, let me just show you what that looks like. So here I'm showing the first 5 complaints in that data set. It's things like open date, blah, blah. Seriously, it's been a month since I investigated, whatever. So then, some choices you have when you're building this co-occurrence matrix are things like, hey, do you want to use all lowercase? Do you want to keep punctuations in there? Do you want to leave numbers in there, etc.? And it's more, the most pure way to do this is you leave these sentences as they are. You leave the text as is and really go learn the true relationship that way, with all different combinations of the word company with a C capitalized or not capitalized, etc. In our case, I'm not going to do that. I have done some pre-processing of the text here. So I made everything lowercase, and then by using this command here, I'm able to get rid of things like I'm getting rid of numbers, punctuation, and brackets and parentheses, etc. And then I see a bunch of this XXX here. That's because this is a publicly available data set, so it's anybody can go see it. Many of the customers, actually some of the customers will actually provide their account number to CFPB that in my account number 12345 there's been some issues, blah blah blah. So they X those account numbers out as they should. So I want to get rid of those XXX, which I do, and so finally we're left with just all characters here, right? And everything's lowercase. And then so what one has to do is basically create this to build the co-occurrence matrix. You have to first create a dummy. Think of it as a dummy matrix, but what size? So what I have to do is I have to figure out how many unique words are there in this 4,300 some comments. So there are 9,638 unique words. So we have to build a co-occurrence matrix of 9,638 by 9,638, and that's what this little code here does basically. And we've just initially filled them all up with zeros, so a whole lot of zeros in that matrix, right? So then what I've done is, here's the code, and by the way, I will leave a link in the description that will take you to this code on GitHub. Okay, so if you so desire, you can download this code from GitHub and play around for yourself, to further your intuition behind word embeddings, and that would be the motivation for why you would want to download that. So here's the function that actually creates the co-occurrence matrix. I already ran this thing because it took 50 minutes to do this. In this example, I made the window size of 10. And I forgot to tell you earlier. So here's something else to keep in mind when it comes to window and scaling. Generally speaking, longer longer the context window and using a flat scale together. So longer the context window and keeping the scale using the flat scale will capture more semantic information. And if you use a small size window and you scale it, then it will capture more syntactic information, so like grammatical stuff. Okay, that's just something to keep in mind. Generally speaking, that's the intuition behind, like, or some of the reason behind why you would want a window size of like a 10 versus a 5, or a window size of 20, etc. Anyway, so just some extra knowledge behind why what window sizes and scale does. So we ran this. It took like 50 minutes to build the matrix, and here's the shape of the matrix. It's still 9,638 by 9,638, but it's no longer going to be zeros in there. So like the word A here, 31,076 times it shows up, because A by A is just basically, you remember when my context word was Python, by default you just give it a value of 1. But it also so happens the word A shows up within a window size of 10 near abilities, so twice. 29 times the word A, or the character letter A, shows up 29 times near the word ability. Okay, so that's basically what this is. The populated matrix looks like. It's going to be a sparse matrix, or in other words, there's going to be a whole lot of zero, because the word A may not show up next to things like Zales and zinc and whatever else. So most of the values in this 9638 by 9638 matrix are zero. A sparse matrix is what it's known as. All right, so we're going to skip through all of this stuff now. Look, we have at this point in time a co-occurrence matrix, a very basic foundational co-occurrence matrix that was built from taking some 4,300 comments, and we built the co-occurrence matrix with a window size of 10 and with a flat scale. All right, so let's see how well it does in terms of finding the word relations. Okay, so in that co-occurrence matrix, I want to here look for the word credit and say, in the co-occurrence matrix, what are the 5 words that have the highest word relatedness with the word credit? Okay, so now that we have this matrix, what happens is that each word, so a word like credit, is going to have is a vector now, because it's represented with numerical values, such as the word A here now is represented with a numerical value with a vector size of 9,638. So each vector has a dimension of 9,638. So now that we have every word has a vector size of 9,638, we can find the 5 words that are most related to the word credit by taking each vector. You can take any 2 vectors and find the cosine distance, and that's what we're doing. And I'm not going to get into, like I said, math here, but this function here, which you'll have this in the code that I give you. There are 2 different ways it allows you to measure the distance between 2 vectors: cosine distance here, or Euclidean distance. The default way of doing it is cosine, but to build your intuition, you should try Euclidean and see how does it do better, just the same, or worse. Okay, so here we go. I'm going to run this little thing, and it's going to give us the 5 nearest neighbor to the word credit. And how to think about this neighbors again is that which are the 5 words in this co-occurrence matrix that that have the closest relationship to the word credit. And so report my bureau's profile erroneous. All kind of makes sense, right? What's really amazing is that this is the most foundational way of building word embeddings through a co-occurrence matrix. And in the world of banking or in finance, this is what you would expect. Like, intuition would be that the word that shows up the most next to the word credit is report, my credit, credit bureaus, etc. So it does really, it does a good job, right? There are a couple of challenges. One is, like multiple times I already mentioned, that it's a 9,638 by 9,638 matrix. So, anytime you have something that big and you have to compute things, there's a lot of computational power that goes on, and it's not the most efficient way of doing it. So we'll correct for that in a little bit. And so one other thing I want to show you here is that the word orange is nowhere in this data set, so it should say false. That means the word orange does not exist in those 4,300 sentences. Well, if I had put the word orange in here, I would have gotten this little error. This is not in the vector space. Later, I'll show you how to correct for that, okay? And so the next thing is, all right, so we have a very simple co-occurrence matrix. Is there a way to, make it better, right? So, there's this concept of reweighting, and we're going to apply some reweighting to our original co-occurrence matrix, where we just took a flat, scaling and just gave a value of 1 of all the words, 10 words to the left and 10 words to the right. So why do reweighting? It helps. Reweighting can help amplify the important and the unusual, relationships in our current co-occurrence matrix, which has a raw count. It's known as, it's basically it's raw count or frequency of how words show up next to each other. So it can help. Reweighting can help amplify the important and the unusual, and it can also help de-emphasize sort of the mundane and the quirky things in our current co-occurrence matrix. Okay, so let's run this, and here I'm using observe. What I want to do is I want to use this PMI, stands for point-wise mutual information, PMI reweighting technique, to take all the values in our current co-occurrence matrix and reweight them. Okay, so in order to do that, I use observed or expected first, because PMI, and I'm not going to get into math, PMI is basically just a log. PMI is really observed or expected in a log space. Okay, I'll just leave it at that. So we ran that. Let me show you this so we can compare things. So now the word A by A has a value of 1219. If I come here to the original one, it had a value of 31,000. So we have reweighted this basically to amplify amplify values which are larger than expected, and through over an expected technique. And then we have also amplified the important things and idiosyncrasies in our original co-occurrence matrix using PMI. So now you see this sort of values. They're not as large. We have reweighted them. Okay, I'm going to spare the math, but if you're interested, go learn more about or expected, observed or expected, and PMI reweighting techniques. Okay, so now that we have reweighted that, let's use the same word credit to see which are the 5 most related words in the new revised co-occurrence matrix. Report, my, bureau's reporting score. Yes, it's pretty much the same ones. Instead of erroneous, we're getting some other things if we don't have profile. Okay, so you have the code. If you want to, you can go run this and see for yourself how all this works. So yeah, it did pull in a couple of different words. It pulled in reporting. I don't think it was in here before. So which makes sense actually. credit reporting. Banks do credit reporting. And then so that was the first technique. We reweighted things. Now let me get back to that point about the dimensionality. It is not efficient to be working with is what's known as a sparse matrix. In this case, our matrix is 9,638 by 9,638, right? That's because I limited my original text to 1% of the total text. Had I used all of the 430,000 plus text, I mean, it probably would have been like 130,000 unique words, and we would be dealing with 130,000 by 130,000, and computationally it just gets expensive, it's inefficient, etc. So can we reduce the dimensionality and yet not lose the semantic information or the semantic relationships between all the words, all the unique words? So in our case, we're going to use the most widely used way to do this, which is latent semantic analysis, and or it's known as LSA. And LSA is usually the baseline, standard baseline in creating word embeddings, and it's usually actually really good. It's often very tough to beat LSA with some other more complex techniques. So while it's running, let me tell you just definitionally LSA, right? What it does. So it's going to take, in our case, the 9,638 dimensions and reduce them to 500. So what we will have is a matrix of 9,638 by 500. Before, each word had a vector size of 9,638 dimensions. Now we're going to shrink that down to 500. But this technique what it will do is that it will retain that semantic relationship amongst these words, and that's the goal. That's what it does. And so now let's just again, we're going to stick with the word credit. Now what we have done is, first we started out with the most basic co-occurrence matrix. We reweighted it. So now we took that reweighted matrix and reduced the dimensions down to 500. So let's run and find the 5 closest words that are related to credit using this technique. Credit scores, profile, updating, monitoring, report. And so what it's doing here is that it's starting to, through all of this, this is more or less what makes more sense in real life. I work in banking, and it's, what I would expect are things like, hey, credit has to be a lot more related to, things like updating the credit reports, credit scores, credit monitoring, etc. And so, I've given you the code. You can download whatever data you want, and the best way to learn is like use my code to create your own word embeddings and build up the intuition. But I'm trying to give you a very high level intuition. So by reducing the dimensions, we still kept the relationship, but in doing that, it starts to actually pull the words that are for credit. It starts to pull the words that are much more related to the word credit, like in real life, like the word my, and things like that doesn't really matter. What I'm looking for is, credit is related to profile updating, those kind of things. So it's more useful that way. I'll let you linger on that and think about that. And so what we're going to do is, I'll just use the word credit here. We can see all 3 techniques, sort of side by side here. So I'm still going to use the word credit and using all 3 techniques. The first one is the very basic, very basic co-occurrence matrix. And the word credit, what are the 7 nearest neighbors, using just the basic co-occurrence matrix. We reweighted it using that matrix. What are the 7 words most related to the word credit in that matrix? And then taking that reweighted matrix and applying this dimensionality reduction method, LSA. What are the 7 most related words to credit? And then, I'm giving you the code. You could put in different words and see, how it performs. All right. So the next thing I wanted to show you here, and I'm going to start running this, is say, okay, I have 500 dimensions. I want to further reduce it. I'm going to reduce it to 300. One of the ways to do it is applying a deep learning, a machine learning technique to do this. It's called autoencoders. And basically, all these autoencoders are doing is it's taking, let's see if I can, let's do this. Let's scroll up here. In our case, we had, let's say, 500 dimensions in it. Let's just imagine this is a 500 dimension matrix. I want to input this into some sort of a deep learning technique, in this case autoencoder. What I'm asking this technique to do is say, now take this 500 dimensions and create a 300 dimensions in such a way that when this 300 dimensions are projected back out, it should replicate exactly this. So what I'm asking the technique to do is go learn this 300 dimensions in such a way by squeezes 500 dimensions into 300, but spit this back out, and I should get the same dimensions as before. If I can do that, I've learned how to compress 500 into 300. Again, guys, I'm not going to get into too many technicalities, but essentially that's what we did. All right, so that's been done. Now we're going to do the same thing. All we did was, what we've done is we reduced the 500 down to 300, and the idea is that we would retain those semantic relationships as before, but we have reduced the number of dimensions. Oops, I already done that. Well, I don't know why I did that. It should run pretty fast here. And then once it's done running, we'll print the 5 nearest neighbors for the word credit. Okay, so while it's doing that, let me show you what would happen here if I had changed this to word something else like mortgage, right? Would definitely be in this text. So if I use the word mortgage, the different words. Freedom Mortgage is one of the largest mortgage providers. All right, so this guy's done. So we're trying to kill time there. All right, the 5 most related words to credit using autoencoder. So what we did was we first started out with the original co-occurrence matrix. We reweighted it, and then after we reweighted it, we applied dimension reductions, a dimensionality reduction to it, reduced it to 500 using LSA. Then we took that matrix and reduced it down to 300, and that's what this guy is. And using that matrix, what are the 5 closest words? So bureau, report, not, remove, my. Okay, so once you have this code, you can try different words. I mean, at a high level, it looks like, hey, I don't know, LSA looked a little better, but that's just one word. Overall, you have to use many different words and do some more evaluation. And so we'll just skip through all of this. And here's a way where we can, remember, the word orange did not exist in the original database, but in reality, what happens, especially today, all these large language models, the way they're built is they don't actually create word embeddings at the word level. It's known as token. There's a technique called BPE, byte pair encoding, basically subwords. So each word is chopped up into smaller chunks, and we build embeddings for those little tokens. And so that's what we have done here. That's what we're going to do here is quickly take our 9,638 words and create subwords out of them. So the word accordance, right, got broken up into like AAC, and I'm not going to get into the byte pair encoding sort of method or technique here. You can look it up for yourself what subwords are. But by doing that, what happens is I can actually so accentuate equals character level rep, and character level rep is just this function here. For those of you who know a little bit about Python, it calls that function and looks up the word orange. So let's see. And so the word orange actually has now a vector, although it didn't exist in my original database, but in the new database that I created with subword technique, there is one. And so similar to for the word count. Now, just for the heck of it, I'm going to take the cosine distance between these two words, 0.308. So again, this is meant to show you that in today there are ways to overcome the fact that your text is not going to be exhaustive in terms of the vocabulary, and plus misspells and everything else, right? So the way this more current techniques like the more current models like GPT and Google's Bard and others, the way they are built, they also use word embeddings, but they actually build the embeddings at the token level for a good reason. This as a side note, but it's like a bonus for you guys. Okay. In my code, I've built little functions like this, or little snippets like this, where you can take different words like word bank and loan. It will give you the distance between these two. If you were looking for distance, here's another little snippet I built for you guys. If you just wanted to find the nearest neighbor, neighbor for the word fees, it's overdraft. You can play around, put in different words, and I don't even know if this is going to work, but this was meant to do sort of an analogy kind of thing. If home is to equity, then credit is to credit. That's not. Yeah, I'll just see what's going on here. But yeah, I'll make sure when I load this code that it's actually working. But it's supposed to be doing analogy. Then the nice thing is once you have word vectors, right? So these are numerical representation. And I'm just playing around here. So I'm saying, okay, give me a word like checking and give me a word like fees. I'll go find the embeddings for the word checking, the word vector, and I'll go find the vector for the word fees. I'm going to multiply those two things and divide by 2. Why? I'm like, okay, if you marry up checking and fees, the marriage of those two words is what? So you can start to do this kind of things. Checking and fees, then you get advantage if you combine these two words. Basically, I multiply those two vectors and divide it by 2. I don't know. You can divide by 3. But it's once you have numerical representations, right? You can start to think about what if I gave it a sentence, right? Checking account. I want to close my checking account, and I could go look up the word embeddings for each one of those words. Maybe I can take an average. Maybe that's the average of the sentence. Then if I do that, and then I take another sentence and do the same thing, how close are those two sentences? So think about that, right? Linger on that. So those are the kind of things you can do, and that's essentially how you can start to do some natural language processing work with this word embeddings, and that's why word embeddings are important, because word embeddings are required for us to do natural language processing tasks like summarization and all the other different things, sentiment analysis, etc. But this is a very basic and basic way of building word embeddings, and then you can still use these things like I just said. You can take any sentence, take each, go find the vector for each one of those words in the sentence, take an average, I don't know, do some mathematical computation, take another sentence and see how similar they are, because you would kind of know are they similar or not, and and then you can play around with different ways of computing that. Okay, and then one last thing I'd done was I had actually built I also built word embeddings using a neural net. And in this case, I had used a technique. I used a technique known as LSTM, long short-term memory model, a neural net model I built, and I basically created for those 9,638 unique words. I created 300 dimension vector using a neural net, and so basically that's what this is. And then if I if we do this word embeddings here, we're going to compare all of them. So this is the most common, the most basic matrix we first created, the top 5 neighbors for the word credit. The next one was we reweighted this original one. And so what are the top 5 neighbors for the word credit? Then LSA, we reduced the dimensionality. Here we further reduced the dimensionality using autoencoders, and then using LSTM. And just quickly linger on the fact that how this guy did. So for the word credit, the 5 nearest neighbors are debit, identity, trans, it's TransUnion, FICO, unlock my credit. So guys, I mean, I'm trying to build a high level intuition here, but you should try it out. What has been known is that when you start using very, very deep neural nets, and they get better, they actually do a much better job of creating word embeddings than the simple methods that I showed you, co-occurrence matrix, even reweighting them, dimensionality, reductions, all that stuff, right? In today's world, ChatGPT is built using what's known as the transformer architecture, a very deep neural net, etc. It doesn't actually embed each word. It chops up the words into tokens, and it creates embeddings for those tokens. But the technique that it uses is so much more powerful. If you use ChatGPT, you know how powerful the thing is. The bottom line, word embeddings are the bread and butter of language models. Actually, they're the bread and butter for all things natural language processing. They are the bread and butter, so that's why they're important. Hopefully you found this helpful, and got a sense for what word embeddings are, and how you go about building them. I will leave the link to my code in the description, so if you want to go play around with it for yourself, do so. Hope you enjoyed it. Until next time.